Greetings. Today we're going to talk about uncertainty calculations, and basically what this involves is looking at the effect of measured values and the uncertainties you get when you take a measurement and how they have an effect on calculated values. And so what we want to do is get a handle on this, and there are rules and regulations for doing it, but for right now we're going to use a technique that I lovingly refer to as the brute force method. Now, the brute force method works all the time. It just is very tedious and can take a long time to do. So again, we want to make sure that we know if we take something that's measured and we calculate something, what's the effect on the final result based upon all the information that we have here. So the example that I am going to use is looking at the dimensions of a piece of paper. And so a regular 8.5 by 11 piece of paper. However, I made the measurements using a ruler so that the values become 27.99 plus or minus 0.02 centimeters. And the 0.02 centimeters comes about because of the divisions between one line and the next on the meter stick, and I can estimate a little bit, and I feel comfortable that I could repeat this measurement and get within 27.99 high by 0.02 or low by 0.02. For the width, the same idea applies, 21.66 plus or minus 0.02 centimeters. Now, once I have the dimensions of the paper, I could also do things like find the diagonal, find an angle. I could even look at what I'm calling the trim piece. I'm going to remove or cut off a piece to make this a square. And I'm going to look at all the different properties mathematically that I can use uncertainty calculations for to see how I can get an uncertainty in the final result. Before doing that, one of the things that I want to make sure we are clear on is that we are dealing with a value that can range for the length from 27.97 to 28.01. That's what I mean by plus or minus 0.02. The same is true for the width. It's 21.64 all the way up to 21.68. So we've got to keep that in mind, that I can have a low value and I can have a high value, and how does that combine when I do my math? So the one math that happens quite frequently is looking at conversions. And so we have our length, and it's in centimeters, but we know that a lot of times we need our length in meters. So we would have our one length, our high length, would be 27.97 centimeters, which is the same thing as 0.2797 meters. And in our low value would be got these backwards, high, low, and then this would be 28.01 centimeters. After conversion, 28.01 meters. And so I have gone above the length measurement by 0.0002 meters, and I've gone below it by 0.0002 meters. And so my uncertainty in the length would become 0.0002 meters plus or minus, because I could go up by that amount or down by that amount, which is the same thing as taking the value for my uncertainty and converting that. So all I had to do was divide my value by 100 to convert my value to meters, but then I can also do the same thing for simple conversions, just divide by the appropriate constant. But then there are other constants that you have to worry about. What if I wanted to double the length of my piece of paper? And so if I wanted to look at 2L, okay, 2L would end up being 55.98 centimeters. But if I put in the low value, so 2 times the low value, I would get 55.94 centimeters, or a difference of 0.04 centimeters. And if I did the high value, I would get 56.02 centimeters, a difference of 0.04 centimeters as well. One is high, one is low, and all I did by multiplying my value by 2 was also multiply my uncertainty by 2. So when I'm dealing with constants, whether it's for conversions or multiplying my value in an equation, then I would just multiply my uncertainty by whatever the constant is. So more happens than just simple constants. So if I wanted to find the perimeter of my piece of paper, I could write my mathematical equation as 2L plus 2W, and I could calculate the perimeter. In this case, I would need to put in, if I wanted to find the biggest value for the perimeter, I would find out what the highest value is for my length and my highest value for my width by looking at my ranges, and add those two together. And I always have to have paper, because otherwise I would not remember. So my highest value would be 99.38 centimeters. I can do the same thing for the lowest value. And when I calculate that out, 99.22 centimeters. So I have a range of values where my calculated value should reside. So when I calculate this out, just based on the values that were measured, then the measured value would be 99.3 centimeters. And I can see how high this is deviated from the measured value, how low it's deviated, and I can see that this went up, could go up as high as 0.08 centimeters or down by 0.08 centimeters. So this becomes pretty easy to determine the range and also the uncertainty. My value is somewhere between those two extremes. We've seen what happens with the property of addition. Now what we want to look at is what happens when you have subtraction taking place. And in this case, the example I'm choosing is to take the rectangular piece of paper and trimming off enough so that it becomes a square. And so we can again look at our situation in terms of we want to find out what the biggest trim value we could ever get. And we have to look at the numbers just a little bit carefully, because now if this is really big and this is really big, I get a margin. If I make this really big and this really small, then I get a bigger margin. So instead of taking high and high, I'm going to take high and low, because then that should give me the biggest margin possible for this trimmed piece of paper and when I'm looking at the values. And so substituting in the ranges that I had posted earlier, the highest value that the trim piece could be would be 6.37 centimeters. Likewise, if I'm looking at the lowest or the smallest trim piece, then I would want to take the smallest length that I could possibly measure and combine it with the highest width. And that should give me the smallest margin possible, which would give me the smallest value for my trim piece. And so in doing that, it's 6.29 centimeters. But when I'm doing the actual calculation for the trim, I would take my values of that I had measured earlier to get 6.33 centimeters. And now I can compare with the values that I could possibly get, and I can see that my range goes up by 0.04 centimeters or down by 0.04 centimeters. And so a good range to pick to take that into account would be plus or minus 0.04 centimeters. So the tricky part is just to make sure that you have a combination that can cover the range of values that you could get by putting in a high value or a low value for the length, a high value or a low value for the width. Not only can we do simple math like addition and subtraction, but we can also do more complicated math, multiplication and division and more. So we're going to look at, first of all, just simple multiplication, in this case looking at the area for our 8.5 by 11 piece of paper. So multiplying by the length and the width, and in this case, I'm going to start off by actually calculating the value that I would get just by using the measured values, and the area would be 606.2634 centimeters squared. Then I can look at the values that I would get if I multiplied out the biggest value for the length and the biggest value for the width. So if these two are big, then my area should be the biggest value. And so I'm going to call that area high. And so multiplying out my largest value that I had for my length, my largest value for the width, I ended up with 607.2568 centimeters squared. And I'm writing all the decimal places my calculator spit out, because I don't know how much this is going to deviate from this one. In fact, in looking at the deviation, I could see that I'm going to call this delta A high, and it deviated by an amount 0.9934 centimeters squared. Similarly, I can look at the deviation for the low end of things. So finding out the lowest value for the area would be using the lowest value for the length, lowest value for the width, and coming out with a value of 605.2708 centimeters squared, or I have a difference between this and my measured value as the lowest end would be minus 0.9926 centimeters squared. And notice that the two ranges aren't identical. There's a slight variation because of the mathematics. So I want to try and pick something that's going to reflect the two ranges that I do have, and yet not get carried away by writing lots and lots of digits, otherwise known as significant figures. A common rule of thumb is to use 1 or 2 sig figs at best. So if I used 1 sig fig, then I could use 1, because I could round this up. When you're doing uncertainties, you always round badly, you round up. So this would become 1 centimeter squared, and that would be okay. But 1 is a really small number, and this is one of the times where maybe using 1.0, 2 sig figs, would be more appropriate. So once I know that that's what I'm going to choose, so that's my uncertainty. And it becomes important to know what your uncertainty is first before you finish writing your values. Because now this tells me the highest level of precision I have available. In writing this as 2 sig figs, I know that the 10th place is the highest level of precision I can expect to have in my final answer. So if I go back to my calculated value, I have to go back to the 10th place, and that's the highest that I can record in my calculated value. And so in this case, I have to round, and I would use the proper rules for rounding a value. So I round badly for uncertainties, and I round properly for calculated values. So in doing so, this becomes 606.3 plus or minus 1.0 centimeters squared. And notice that sometimes I'll write the units after each value, or I can wait till the very end and write the units likewise. After multiplication, it becomes easy to look at division, which is basically the reverse process of multiplication. So in this case, I'm going to look at the property of tangent theta, because if we look at our original diagram, so here's our length, there's our width, I had drawn in a diagonal, and I had indicated an angle theta. Well, a lot of times we want to know the angle, and we need to use trig to do that. Well, trig involves ratios of sides of a triangle. So if I take the ratio of the width to the length, that property is known as the tangent of the angle theta. And I don't really care right now what theta is. I just want to use tangent theta so that I can see the effect on what happens to a division property. So the first thing I'm going to do is look at what tangent theta is using my measured values for the width and the length. And I have no idea where I need to stop, so I'm going to use a lot of digits in my answer. That should be enough. If not, I can write more. And now I need to try and figure out how I'm going to get the biggest value of tangent theta. So I want the biggest value of that whole combination. If I make the width very big and I make the length very small using the ranges, then that should give me the biggest ratio available. And if you don't believe me, you can try by using the combination. You can use the highest width to the highest length, the highest width to the lowest length, etc. and see what happens. In doing this, tangent theta high ends up being 0.7751. I'm going to put it in another place just to be on the safe side, a couple more places. And I can see that the first two places stay the same, and this starts to deviate a little bit over here. So I'm going to find out how much that deviates. Okay. And notice that I wrote this to 3 decimal places because I just wanted to show you, kind of an idea what the numbers are before I finish up my final uncertainty. Similarly, if I do tangent theta low, this is going to be the lowest value for the width and the highest value, and that should give me the smallest ratio possible. Substituting in the values, 0.77258, or a difference of goes down by 0.00127. So I ended up having a pretty uniform, there's some subtle differences later on, but I could get by saying my uncertainty now is going to be 0.0013, and that should encompass all the combinations I could have for the different values for the width and the different values for the length. So once I'm done with that value, then I'm going to just get rid of this, because now we want to be able to see how we take our values and make adjustments. We already know that this is going to be plus or minus 0.0013 to 2 sig figs, which means that this is the last decimal place that I have any faith in the precision. So matching that and rounding properly, 478 doesn't contribute to anything, and my value for tangent theta becomes 0.7738 plus or minus 0.0013. Having found tangent theta, I could go ahead, and I'm just going to slide this over so that I can see the values. I can go ahead and now use trig to see. So now I would use the calculator function that has the inverse tangent and calculate the highest angle I could measure, or calculate the lowest I could calculate, and then see what the ranges are. So if I look at what the theta would be by using 0.7738, and drum roll please. It's 37.7327 degrees. Using my highest value for tangent theta, doing the inverse function on that, 37.7793 degrees. My lowest value would be 37.608. And I can see that my uncertainty, the deviation from the highest value, would be 0.0465. Well, now that's a problem, because now I'm starting to tell you 3 sig figs, and in the past, the most I've ever used is 2. And I used 2 because 0.00127 was on the small side, and writing that as 0.002 to 1 sig fig would be just too high. So I left it as 0.0013. Here, I'm going to go ahead and say, well, this is 465. That's actually closer to 5. And now it's a bigger number, and I'm going to keep that to 1 sig fig. Same is true for the low value. It ends up being 0.466, which can round to 5. So both of these, now we have a uniform high and low, and I am ready to write my final answer. Rounding properly and keeping it to the 100th place. So my final answer is 37.73 plus or minus 0.005. One more. The last item that I looked at was looking at the diagonal, because now we're doing more complicated math, and we are trying to include what happens when we square values as well as taking square root. So using Pythagoras' theorem, I should be able to get the diagonal dimension and then be able to use that to look at the high and the low values. So in calculating D, substituting in the values that we've been using for the entire practice, I obtained 35.392. I'm going to go one more place just to be on the safe side, and then that would be in centimeters. I would look at the highest value, because it doesn't take much to look at. If I square L high, then I'm going to get a big value. If I do the same thing for the width and then add them, I'm going to get the biggest value possible before I take the square root. So if I use the high value everywhere here, I'm going to get the highest value for the diagonal. And the highest value for the diagonal is 35.4200 centimeters. Doing something similar for the low value, I obtained 35.3640 centimeters. And I can look at the deviation, the high value. How much does this deviate from that? It's higher by 0.028 centimeters, because I'm not going to write more than 2 sig figs. I now have a choice. That might be 0.028, or it could be 0.03. But before I decide, I'm going to see what happens when I do the low end. And it's also 0.028 centimeters. My preference is that this is still on the lowest end. So that the 2 is the leading number, and that's what I use as a rule of thumb. If the leading number is a 2, I use 2 sig figs. If it's a 1, I use 2 sig figs. Any other number, I keep it to 1 sig fig. So putting everything together, I have now a value for my diagonal. And so keeping 2 sig figs for this particular situation, I would have 35.392 plus or minus 0.028 centimeters. As I said earlier, this is very tedious to do. You have to do this for every possible combination and in every step of the mathematics. In future videos, we will talk about how you can go ahead and do these calculations using calculus to determine what the actual values are. In the meantime, have fun calculating the uncertainties that you get in any of your answers.